Hello, our names are Connor Alfonso and Nelson Manstein, and today we're excited to share our project, Convolutional Neural Network Identifying Simulated Breast Cancer Lesions with Novel Localization Technique. This project was born out of a desire to undertake an engineering project in healthcare that could significantly impact the global healthcare. In our research, we learned the extent of a global health crisis, breast cancer. In 2022 alone, it caused 670,000 deaths worldwide and was diagnosed 3.2 million times. However, early diagnosis and appropriate treatment can greatly improve survival. The bad news is that there is a large disparity in diagnosis and mortality in high-income countries compared to lower-income countries. The top global map from Huang shows the density of diagnoses with darker shades of blue, indicating that high-income countries are more likely to diagnose. Mortality is shown in the lower global map, which shows a reverse, where the mortality is higher in under-resourced countries, as shown in the darker red shade. So, why this paradox? One of the main reasons for the higher diagnosis leading to lower mortality rates is that the under-resourced countries are not able to diagnose breast cancer in a timely fashion. So by the time the diagnosis is made, the cancer is too invasive to be treated. The highest mortality rates are in under-resourced countries, like Melanesia, Polynesia, and parts of Africa, where many people lack access to diagnostic tools. In fact, 3 to 4 billion individuals globally don't have access to radiology services. So that's where our project comes in. Currently, mammogram and biopsy machines cost upwards of $400,000, and a single mammogram and biopsy can cost between $600 and $1,400. We designed a proof of concept device for just $200.24 that can identify and localize breast lesions with remarkable accuracy. The idea is to create an inexpensive way for a mammography expert to guide a mammogram biopsy machine, only requiring a trained technician on site. Understandably, we cannot use real patients because that would be unsafe for them, and we cannot use x-rays because that would be unsafe for us. Since x-rays were first invented in 1895, this is a well-understood technology that can be recreated inexpensively. Here's how it works. First, we simulate mammograms using gelatin molds embedded with small rocks to mimic lesions. 2 Raspberry Pi cameras capture orthogonal views of these models. Then, a convolutional neural network was developed to analyze and detect the lesion. The neural network then draws a bounding box around the lesion and calculates the center of the lesion. Google MediaPipe and Label Studio were used to make the convolutional network. The resultant neural network had 426 layers and 246 nodes, and is diagrammatically represented here. And here is an example of it working with our gelatin simulation. Before the image is taken and the neural network is deployed, we first calibrate the machine. Using this 3D printed calibration device, a picture is taken. Each yellow dot is a known location in space, and with the image acquired, each pixel corresponding to the center dot can be matched to that known location in space. So we get a grid with 9 known pixel location combinations. This is enough to assign each pixel a known point in space. Knowing the number of pixels between each known pixel, one can extrapolate the real-world location of all the pixels in the calibration device's plane. Using the points on that plane and the center of the camera's lenses, we can create rays from the camera's center to the known real-world position corresponding to the pixel location. Remember, we have an orthogonal 90-degree apart view. We can use this view to create a second ray around the center of the bounding box from the second view. Parametric equations can define these rays, and the intersection, or closest point to the intersection, represents the center of the lesion in the real world. Since currently available mammogram biopsy machines use stereotactic localization, where the images are not orthogonal, this localization technique represents a novel one. Then, 2-step motors actuate a laser pointer to mark the lesion's position on the surface, while the system also predicts its depth. So, how good was the neural network? And how accurate was the localization? The sensitivity was 90.4%, and the specificity was 93.8%. Our system localized lesions correctly 85.8%, or around 103 out of 120 hits. The 17 misses had an average error of just 0.6 centimeters. This project represents a proof of concept to drive down the cost of breast cancer mammograms and biopsies. The whole project was completed with off-the-shelf products. The breakdown of the cost can be seen here, with a total cost of $200. Thank you for taking the time to learn about our project. Feel free to ask if you have any questions or want a closer look at the system in action. Thank you again.